Hello, everybody. Danko Nikolic speaking. It's a pleasure to be here. I'm going to give you a talk that's related to AI, but also related to neuroscience. So a few things about me. Important thing is that I have been a neuroscientist for most of my adult life, for most of my career. Only in the last few years or so, last 5 years, I have been involved in developing artificial intelligence solutions and using artificial intelligence technology. And of course, I cannot help myself but think what I know about the brain and apply this to AI. So I want to tell you something quite interesting today. And let me share my screen for that. Right. So some interesting properties of the brain that AI should take a note of. So we all want to improve AI, and the brain has a lot to offer. So I'm offering here, telling you about 3 principles, 3 new properties that are really important that the brain uses according to my research, and that AI today still does not use. These 3 new principles are surprising, and here they are. Deep, long hierarchies are not the most important part of the brain. The brain has also something similar to deep learning, something to deep architecture, but it's not the most important part. It's not the very nature of the brain. Something else is the very nature of the brain. Number 2, maybe most surprising, synapses don't matter that much, right? Everyone thinks that, everything's in synapses, but not necessarily. Let's see. And number 3, simple and clever learning mechanisms are not sufficient. So learning mechanisms that we use today are relatively simple. It's like one equation, one formula. And it's not how the brain develops itself. It's not how the brain learns. The brain has much more elaborate learning system. I will talk least today on the learning system. I will spend most of my time discussing the first 2 topics. So maybe you have seen this picture. This is a traditional view of this deep hierarchy in the brain. So we have retina, which is in the eye. Then the signals come into thalamus, a part of thalamus called LGN. Then comes in the cortex, V1, V2, V3. These are all different stages in the cortex, and so on, right? So according to these images, probably we have built some of the deep learning architectures in artificial intelligence. But this is, as I'm saying, not the most important thing, right? Here we see illustration of what we do in deep learning, something similar to that. We put lots of layers, input layer, and then processing the stages information until the output has been generated. Right? But the brain, human and animal, has lots of very short circuits. Like you see here, a reflex for patellar reflex. So probably everybody knows what a patellar reflex is. When a neurologist hits you under the knee, your leg jerks. Right? So it's a very short circuit. But it's not only that. For example, your eyes and the eye muscle are also closed in very short circuit. It's also sort of a reflex, right? And a lot of the control of the eye comes from very simple reflexes. But it's not all. Like when you look at the cortex, like here up there, we have a cortex, here we have a thalamus and LGN that I was mentioning, and the eye. Much of the connections are not deep connections, but the signal comes to the cortex, to neuron to the cortex, like you see up there, and then immediately this neuron feeds down back to, say, superior colliculus, which is a part that's going, after that is going pretty much straightforward to muscles. A very short path. And actually the brain is mostly built of such short pathways. Here we see a general principle, how the brain is connected, what I want to tell you about. You have one reflex down there going on, you have another reflex down there going on, and they're somehow connected with the cortex, but through very short path. The information goes up and goes immediately down. That's a different type of connectivity than what you have, than what we have in deep learning. So deep, long hierarchies are not the most important part of the brain. The brain is shallow, it's not deep. That's pretty interesting, right? The brain is, in fact, quite shallow. And to realize how shallow it is, it's a very good example is the octopus. The octopus first is very intelligent animal. It's like surprisingly intelligent in animal that can use tools like here an octopus is using coconut nuts to protect itself, to build a shield. Here's another way of building a shield by using shells or whatever, stones and materials. They're quite creative, they can do quite a bit of things. And the interesting thing about their anatomy of the nervous system is that they don't have really one brain, but they have like 9 brains, because each leg or each arm, whatever you want to call it, from octopus, they're called not arms, I think. So each arm has its own nervous system, its own brain, pretty much. And there is one central one that's connected to the eyes, but it's not that much bigger from the rest in terms of count of neurons. So the interesting thing is that the octopus manages to achieve all these tasks. It coordinates 8 arms. Imagine coordinating 8 arms, it's not so easy. I mean, we have 4 to coordinate. Coordinating 8 is probably a bit of a harder problem. But they manage it in a distributed manner where each arm has its own brain, and each brain has its own reflexes and that I described up there and so on. It's a very different type of architecture than what we are used to in deep learning. Okay, so that's the first problem I thought. Now let us move to the second problem. Let's talk about synapses. So this is a traditional way of thinking about it. Right? We have here the gray parts are the inputs from the other neurons. They have some sort of synaptic weights. So some synapses are stronger, some are weaker. Now stronger synapses produce stronger input. All these inputs then sum up somewhere in the body, and then the neuron is sending output with some thresholding and so on. That's the classical view, and that's what we are copying and using in deep learning. Like, for example, in this network, all of these little endings of the lines are these synaptic weights. And what this network needs to do in deep learning is train the synaptic weights. Once you have trained the synaptic weights properly, you have a proper performance. So the intelligence of this network is stored by the synaptic weights. So let me make a claim, a crazy claim. Neurons themselves are smart. They have smart wires. This is where intelligence of real neurons comes, not from the synapses. Synapses are important. Sure, they have to bring some information. They have to send information forward or backward, whatever. But it's not where the intelligence is, our own intelligence, where my and yours intelligence is. It's in the intelligence of neurons themselves. There are machines that are smart. And what do they do with this smartness? Well, what they can do, they can monitor what's going on. They can look at the context of what has been coming into the neuron in the past. They can look out they can learn what has worked in the past and not. And then they can decide, I'm gonna close this branch of my dendrite. So I'm gonna close this wire for a moment. And I'm not gonna let any inputs come in. And it's not about synapse, it's about neuron itself, closing one part and letting maybe inputs coming only from the other part, right? In fact, here's a stronger claim, only a small subset of the entire biological neural network is active at any given moment. Most of the things are closed, and then here and there the neurons open something and like, for a moment, things go through. That's what they do, believe it or not. So most passages are closed. And the wires of the neurons, the dendritic trees mostly, and the soma, the body of the neuron, they're smart enough to control opening and closing of pathways. So here, for example, right, you could pass, given the anatomical connections, you could pass from left to left or from left to right, and so on, right? So which one do you choose? Well, the neurons can choose themselves. They have enough knowledge and wisdom and experience to make these choices. That they make these choices. They make these decisions on which parts they were close and which parts they were not close. So let's compare the classical paradigm, which is called connectionism computational encoding, with this new paradigm that would basically emerge out of these changes. And so the classical one, we have connections. We said the connections determine the computation. The steps of computations are neurons that code for something. So when the neurons has output, that's the result of a computation, according to the classical paradigm, right? And now, by using this paradigm, we have also factored quite a bit of neuroscience. In neuroscience, we use the same paradigm, right? So we used, we created experimental designs, we selected data, we analyzed data, interpreted the results such in a way of this paradigm. So it kind of these other things got hidden away. These other properties of the true nature of the brain got a little bit hidden of the way. That's why neuroscience did not directly so effectively influence the AI field. And here's some of my own experimental results that have helped me, create these insights. So here's you see on a time how time passes when we present one stimulus in a neuron in a visual cortex in V1. And here the gray square is the time during which we have presented the stimulus. And now there was one really surprising result, amazingly surprising, and at the beginning annoying result we had. During the presentation of the stimulus, we had, the activity of the neurons. They couldn't tell really well what was the stimulus. Like if the stimulus was letter A or letter D, couldn't tell really. The signals couldn't tell really well what the difference was. But once we removed the stimulus, then we had very good. Then the activity that remained in the neurons was able to tell us quite accurately what the stimulus was, when the stimulus was gone, not why the stimulus was there. And back then, I didn't know really how to understand these results, but now after some years of working on it, on these problems, I realized that this is because of this intelligent, smart wires of the neurons. They take the time the stimulus is there to rewire themselves, and then later, whatever the effect they had of this is visible in the activity of the neurons, whatever effect they had in changing the wiring of the network. And here's evidence that, even stronger evidence that something like this is happening, right? So here we have a sequence of three letters. Gray is like we presented one, A or D, and then we present maybe B, and then we present after that C. And now what is interesting, like when we present A or D, we can't tell whether the stimulus is A and B, A or D. Cannot tell accurately. But we remove it and then we represent B, and then suddenly it works well. We can detect A while we are watching it B, and also it worked like this. We could detect B while we were watching it C. It was quite crazy. I mean, the information had this back memory of what was just happening a moment ago, right? And if you kind of think of the way how your own experiences work, you will see that this is something very similar to what you see here, not to how deep learning networks work. Right? So let's compare once again, like where the differences are. Look at the right side. Deep learning assumes that connections are deep, complex, elaborate, and connectome matters, but sometimes we call it connectome. Also assumes that neuron membranes are dull, and they sum up things. And there are a few simple plasticity mechanisms or learning mechanisms, right? And we have here three knowledges. Connections are shallow, they're not deep. Neurons are smart. And these learning mechanisms or plasticity mechanisms also have to be smart, as I have mentioned, in order to be able for neurons to learn when to change which connection. They're not born with this knowledge. They actually learn this knowledge. Actually, all our knowledge, that's the claim, all our knowledge, all our cognition is stored not in synapses, but in the knowledge when to switch which connection. And neurons contain this information, but not in synapses, but elsewhere. And here's an illustration of how these different things interact, right? So here the box on the top interacts with the external world the fastest. And this box is basically the neural network without changing the connections. Whatever the connections are set, it's actually producing some reflexes. But then this second one is indicating that the neuron is watching what's going on, a little bit slower, but it's watching going on, and it's then it's changing the connections. It's changing its connectivity, changing the pathways. And finally, the third one is the learning mechanism that is working even slower, and that it's watching the performance of those who change the connections, and it's adjusting them. And that's the you know, when I got to understand this, for me that was mind blowing. That was really mind blowing. It still is mind blowing. How much different this is from what we do in deep learning. All right, here's an example of what's really, you know, another thing. Like, look, if you have, you know, if this is time from left to right, and you have dark and light and dark, you would expect that perfect coder, like something that's the brain that's built on the logic of deep learning would have, you know, would code information like this, like, you know, no light, light, no light. Exactly when the light is there, you signal light. But it actually would, you know, do something like this, something messy, something like this. Like, so, and these events are basically operations where the connectivity change, while the connectivity changes of neurons, and that's the mind, that's our mind, this rules, these mechanisms that within neurons that close and open different pathways make up our mind again. Right? So we have to change the paradigm. We have to start thinking in a different way. The classical view is basically the view of a box, right? You put algorithm and data in a box, you close the box, and you keep the box closed until the computation is complete. But whatever I have told you now, it doesn't work this way. It cannot work anymore like this, right? You have to work differently. So computation in the box hypothesis, let's call it the hypothesis, says that the connections are the algorithm. That input is the data, and it's represented by the activation of a neuron. Then inputs are passing through the transformations, and of passage through the whole stages of processing. That's the end result. And the algorithms are just sitting and ready to go, just waiting for the inputs to pass through. That's the classical paradigm. And what we learn these algorithms, the connectivity, basically. But if we do not think box, then we see that the data are never completely in the box. The data are outside, because you always interact with the environment. You remember these loops. You always have to interact with the environment. The algorithms are never completely in the box. We over time, as we change the connectivity and interact with the environment, we load pieces of algorithms. We slowly build up our algorithm in our head. As we enter some new space, a new problem, we look around and we build up slowly, step by step, our algorithm, how we are going to act in this place. Sometimes it takes longer, sometimes it takes shorter. If it's a familiar space, it's shorter. If it's a less familiar space, it's longer. There's this process of iteration, of looking around and changing gradually more and more our connectivity of the brain. So we create new algorithms on the go, right? And then there is no clear separation between the inside computation and the outside of computation. Right? There's no separation between data and algorithms, and there's no beginning and end of computation. It's just continuous flow of changes and actions and reflexes and changes again of pathways and new actions, new reflexes and new changes, and this keeps going. And like we have described here. Okay, so 3 new surprising principles. I'm going back to it so you remember that. Deep, long hierarchies are not the most important ones. They exist in the brain, but this is not the most important one. What is important is the short connections. Second, synapses don't matter so much. They're important, but they're not critical for intelligence. What is critical for intelligence is something else inside neurons that's not synapses, and that decides when to connect what. It operates a little slower than the activation that passes through synapses and passes out, but it's smarter. It's much smarter. And then simple, clever learning mechanisms are not sufficient to support such machinery, but you need very smart ones. And that's why it took evolution so many millions of years to create human brain. It's not just one algorithm and that's it, right? It's lots of algorithms that actually help us develop quickly, learn quickly, that help a baby learn quickly and develop and acquire knowledge fast. So we have to use those wisdoms in artificial intelligence. That's my final message, and thank you very much.